Last time we started section 10.4, and the part that we had looked at was the part about measures of central tendency. That is how things sort of bunch up or average out over the data that we're presented with. What we're going to take a look at today is how things vary from that bunched up or average value. And the first way that we're going to look at doing that is something called range. Now, you've heard this word before, the word range, in many contexts. So maybe you heard it as in domain and range, right? Or maybe you have heard it in this context. The range for us in this context is simply the difference between the greatest and the least value in the data. It's how far apart the high and the low are. So like if I were to talk about the range of ages of my children living in my home, it would go from 10 to 18, or 19 now, my goodness, 10 to 19, okay? That would be a range. The next piece is talk about quartiles. So quartiles, what they do is they split the data into 4 equal parts, like quarters. Think about like quarters of a dollar. The first quarter, the second quarter, the third quarter, the fourth quarter. Think about quarters of a football game. First quarter, second quarter, third quarter, fourth quarter, okay? So the first quartile is the value, you know, it's the time, basketball does it too, right? Does anybody watch Thunder? It's when the first quarter ends, that's 25% of the game is done, right? So that's what we're looking at when we're talking about the first quartile, is the number that we get to when a quarter of the data is done. And then we have the middle quartile, okay? So the middle quartile would be Q2. It's where 50% of the data is now done. Also could be called like halftime. Or the median. We've already used that one. Thank you. The median. The third quartile would be the end of like the third quarter of the basketball game. 75% of the data has been completed. 25% of the data or the game is to go. And then we have the ending value. There's not a, I mean, it is the fourth quartile. It's just that it's the end of our value, so we don't usually use that one as informational. Okay? There's a couple more, and then we're going to use these pieces of information to create a display. Interquartile range is the difference between the lower quartile and the upper quartile. So like if we were talking about, you know, kind of imagine doing the basketball scores. If you wanted to know the interquartile range, it would be the points that they scored in the second and the third part of the basketball game during the second quarter and the third quarter. Okay, it's all the data, in that case, all the points that are occurring between the end of the first quarter and the beginning of the last quarter. The lower extreme is simply the smallest value, and the upper extreme is the largest value. So those are pretty, they're named in such a way that they sound right to us. We use that language in everyday talk. And then what a box plot does is it creates a display of the data using all these pieces of information that we just described or defined. Uses the lower quartile, the median, the upper quartile, the interquartile range, and then the lower and the upper extremes. So we're going to be using a set of data that we saw last time already. It's a very simplified, I mean, there's not very many data points in it because I'm not trying to confuse you with the data. We could certainly give more data, but I just want us to be able to have practice identifying the pieces of this using the graph. So in order to make sense of any of this, the first thing we've got to do is to put it in order from least to greatest, okay? So restructure your numbers, and again, we've done this one before, so look back at it if you want to do it more quickly. And we had the numbers. It was 12, 17, 18, 18, 22, 22, and 30. And the first thing we're going to do is we're going to use all those numbers and identify each of these different values that I just defined. Now we already did one of them. We did the median last time. What was the median of this set of data? It was 18, and it happens to be the second 18. So there are half of the numbers below it, half of the numbers above it. Everybody good with that? So this is my median. Can you see that green okay? Okay. All right. So once I've got the median, it's kind of like not for consideration in the rest of our information. Now what I'm going to do is I'm going to look at everything that occurred before the median. And I'm going to do the same thing again. I'm going to choose the middle value. Now, this happens to be very nice because there's only 3 values, right? So it's very friendly. What would be the middle value of that first set of data? 17. So 17 would be our Q1, quartile 1 value. We do the same thing for the upper values, the numbers after the 18. What would be my Q3? The second 22, right? Q3. Because we've written them in order as well, we also know that the 12 is my lower extreme, and we know that the 30 is my upper extreme. Everybody good so far? Excellent. I want us to create a number line now. The number line needs to go from 12 to 30. And again, be approximately equally spaced. I'm just numbering every other, but that's not too bad. Okay, all of the values that we just identified, excuse me, in green are now going to get a dot at that value or above that value on my number line. So I need a dot at 12. I need a dot at 17. I need a dot at 18. It's obviously really close to 17. I need a dot at 22. And then I need a dot at 30. Good? All right. The 2 dots on the outside get connected with a line segment like that. And the same thing for the ending one. Okay? In the middle, these 3 have horizontal or vertical lines, excuse me, like this at those 3 dots. So 17, 18, and 22 all have vertical line segments. They should be approximately equal. Mine aren't very convincing, but... And what we're creating is a box right here. Oh, that was terrible. Okay, so this is called a box plot, sometimes called a box and a whisker plot. Can you see the box and the whiskers a little bit? So what you can see very quickly from this data is you can see a lot of how things are spread apart. So you can see that, yes, there's a value that's 30, but it's really not close to most of the values, right? What we know from this data is that this is the middle 50% right here, right? Because it's from Q1 to Q3. It's the middle part of the game of basketball. This is my upper part, right? This is the last 25%. This is my lower 25%. If all I dealt with was this, I'd also know that this is the middle value. This is the median. Half of the values are below this and half the values are above this. So I can see a lot at a very quick glance on this particular plot. Just like with all of our other graphs, we need a name for it. So I'm just going to write title. This one didn't actually have any data given. It was just a set of numbers. But most of the ones you're going to go deal with are going to have data. So they're going to say scores on a math test, or they're going to say precipitation and rainfall in inches, or whatever it says. Or what we did last time, we did the vertical jump heights for 5 starters on some kind of a team. All right, so this is one way to talk about how things are spread apart. It's called variation. Another way is called deviation. There's 2 types of deviation. The first one we're going to look at is mean absolute deviation. This makes use of the absolute value to find the difference each data point is away from the mean. And it's found by taking all absolute value differences and averaging them together. All right, so that's a wonderful word picture, so to speak, but it's probably easier to look at the details as a list. So that's what I've got here next. In order to find the deviation, the first thing you do is you find the mean. Oh, wait, hang on. This is variance. I'm sorry. Let me go back over here. Do I have an example? Okay. Let me show you an example by switching. We'll just go to example 5. That's what I'll do. I had a list, but I have it for the other problems. Mean absolute deviation. Okay, so the first thing you have to do is you have to find the mean. That makes sense because this is mean absolute deviation. So we did that last time on this data already because I'm recycling my data throughout this lesson. What was the mean? It's denoted with a bar on the top of it. That's how mean is notated. What was the mean that we found last time for this set of data? Feel free to flip back. What was it? I think that was the median. 19.89. Okay, 19.89. Yeah, we'll go with 19.9. That's fine. And what we're going to do is we're going to create a table just to organize our data. And it's going to be a table of the scores that we have. So all of them, even if they repeat. So 18, 22, 22, 17, 30, 18, and 12. So this is our X values, or our data values. Let me just say data values. Apparently I'm going to abbreviate to data because values is too far. Look at that. Just move things around. All right, this middle right here, the next column is going to be the data value minus the mean, and I want the absolute value. So what that means is I don't really care which one's bigger. I just want to know how far apart they are. So how far apart are 18 and 19.9? I mean, feel free to grab your calculator and subtract. I would hope that that's okay to do in your head. What is it? 1.9. If I start at 18 and I go to 19.9, I've traveled 1.9. How far apart is it from 22 to 19.9? 2.1, and I got 2 of those. How about 17 to 19.9? 2.9 is right. 30. Close. Yeah, 10.1. 18 I already did before, so I know that one. That's 1.9. And 12? 7.9. So I find the difference that each data point is away from the mean. That's what I just did. Everybody good with that? And then it says I'm going to take all those values and average them. So I'm going to take all those values and I'm going to add them up. So what do I get when I add these together? What's their sum? That's not what I have. 28.9 is what I have written down. 28.9. And then that's the sum. And then how do I get an average for something once I have the sum? I would divide it. So my mean absolute deviation, that's abbreviated MAD, is 28.9. And then I would divide by how many values I have, which is 7. So what is 28.9 divided by 7? Yeah, 4 point something. We'll go with 1 decimal. 4 point what? 1. 4.1. Okay, so that's how you find mean absolute deviation. You find the mean, you calculate each of the differences from the mean, you add them up, you divide by however many you have. Similar process is finding what's called the standard deviation. And the standard deviation is simply the last step in finding the variance. So this is written as though we're finding the variance. So to find the variance, i.e. how something varies, you find the mean. That's what we did for mean absolute deviation. The second one is you subtract the mean from each number. That's kind of what we did for the mean absolute deviation. The third one is you square the differences. And while I didn't say you had the absolute value on part 2, you could if you want, because what happens when you square negative numbers? They become positive. So it doesn't really matter on step 2 whether the value is positive differences or negative difference. It just doesn't make any difference. And then on part 4, you sum them up. Well, that's kind of like what I did just a minute ago, right? You sum things up. You're summing squares, but not the original, but you're summing squares. And then step 5 is you divide by the number of values. So the really only difference, truly, is the fact that you square things. And then if you're actually finding standard deviation, the last thing that you would do is you take a square root. Now you might be thinking, okay, I square things and I take a square root, so won't I get the same answer? The answer is no, because you're not squaring the exact same thing you're taking a square root of, okay? So take a look. Part B, I believe, has us do the same thing as part A, but do it for variance now instead of for mean absolute deviation. So I have all the same stuff to start with. I have X bar is 19.9. And my table, I mean, it's going to look the same. I'm going to have my data values. I'm going to have my column where I find the differences. So those two pieces are going to be the same. So we're just going to repeat that real quick. So I have 18, 22, 22, 17, 30, 18, and 12. And then, so these are my data values. And then I know it didn't say that I can do absolute value, but I can, because I'm going to square the numbers in a minute anyway, so why not? I mean, why worry with the negatives if it don't really matter? And they don't. So I can use those same values I had from my last table. That was 1.9, 2.1, 2.1, 2.9, 10.1, 1.9, and 7.9. It's the next column that actually we didn't have. This one is taking that column, which was data minus the mean, and squaring it. That's different. So grab your calculator, because I don't know about you, but I don't want to square 1.9 and so forth in my head. So what is 1.9 squared? And 2.1 squared. Okay, and I've got 2 of those. And then 2.9 squared. 10.1 squared. I already did the 1.9, that was 3.61. And what is 7.9 squared? All right, so in terms of this list of steps, that was step 3, the square of the differences. Step 4 is to sum that up. So find the sum of this. What'd you get?
188.87.
Is everybody good with that? Okay, so that was step 4. And what does step 5 say to do? Yeah, I would divide by 7. Now, what I'm finding is variance. You can abbreviate it VAR. Oddly enough, it's also abbreviated with the letter S. Don't have a good reason for that. I'm sorry, not S, S squared. S squared. I guess you could say the reason is what comes next, but either way, you've got 188.87 then, and divide it by 7, what do you get?
26.98.
And so if I'm doing 1 decimal, it'd be 27.0, right? That's my variance. My variance is 27. So that's part B. But part C says to find the standard deviation. And standard deviation means to take the variance and take the square root. And this is probably why we use s squared, is because what happens when I take s squared here and square root it? You get s, and s is for standard deviation, so that's probably where it's coming from. So we can do that, right? We need the square root of the 27.0 that we just had. So as a decimal, with 1 decimal of accuracy, what would that give me? 5.2. That is how spread apart the data is. And we'll talk about how that's used as we move into the next piece on this lesson. So what does it really mean? What does the standard deviation do for me? I mean, how does that give me information about how things are spread apart? Well, we have something called a normal distribution. A normal distribution is called the bell curve. Have you ever guys, I know you've heard the phrase grading on a curve. You don't mean it appropriately when you say it. When you say grading on a curve, what you want is you want somebody to add points to all of your test scores or whatever it is, right? That's what you really mean. That's not really what grading on a curve means. When you talk about grading on a curve, this is actually what it's referring to. You've got a bell-shaped curve like this, and somehow the professor or whoever it is decides that there's these marks on here, and all the people who are in this area get A's, and in this area people get B's, and here's the C's, and here's the D's, and here's the F's. So what that would mean is you have about the same number of A's and F's, about the same number of B's and D's, and about the same, and then you got the C's in the middle, sorry. Okay? That doesn't necessarily work at a university like this because we don't have large enough classes for it to make sense. But normal distributions happen all over the place outside of test score kind of stuff as well on how things are distributed. Now, let me actually talk to you about why that's valuable. The empirical rule for bell-shaped curves or normal distributions says that 68% of the data is within 1 standard deviation of the mean. So if you had somebody grading on a curve, the standard deviation marks would be the middle marks right here, and you would have 68% of your class with C's. And I don't think that's really what you mean in general that you want when you say grading on a curve. It's a lot of C's, right? As a professor, I don't want 68% of my students to get C's. That is not my goal. And then you actually have 95% of the data between a B and a D. I don't want 95% of my students to have B's, C's, and D's, right? And then if you go out far enough, these pieces of information out here, then we actually have sort of the rest of the people, 99.8, it's almost 100%. So what that means is there's only 5% of the people on the ends of this little curve who get A's and F's. And it'd be split about evenly. So do you want 2.5% of the people to get A's? No, that's not what we want, but that's actually what it looks like to grade on a curve, okay? So we're going to do something not grades because that's just depressing right there. We're going to do something else that's got a normal distribution, and we're going to talk about, I think it's phone calls. Yes. It says assume a normal distribution. Now, it is important for you to use that language and to recognize that if you don't have this language, it may or may not follow the empirical rule and the data for that bell curve at all, okay? That data, that statement in the sentence is important. It matters. That's what allows me to do what I'm about to do. And then it tells us that the average phone call in a certain town lasts 8 minutes with a standard deviation of 2 minutes. And it wants to know what percentage of the calls last between 6 and 8 minutes. Okay, write yourself a note and tell yourself, every time I do one of these normal distributions, I'm going to draw the bell curve. You're going to have lots of bells on your shapes, or on your problems. So here's your bell with the line underneath it. And I need you to mark every single time that I have one of these standard deviation values. So right here is the mean, and it tells me what is the mean of this information. What's the average length of the phone call? 8 minutes. And then it tells me if I go out one standard deviation in each direction, and your picture does not need to be perfect or symmetric. I mean, in theory, it should be pretty close, but it says that the standard deviation is 2, which means the distance between the mean and the next one out is 2. So what does that put these new dotted lines I drew at? 4, whoa, not 4, 6 and 10, right? I think you went 2, but that's for the next one though, Shelby. So we're going to go out again. If I go out again, they're 2 away, so this would be 4 and 12. And we do it one more time, and where would I be? Don't everybody talk at once. 2 and 14, thank you. Okay, so this is where you start. You start by labeling all of those hash mark values on your table, okay? The next thing that you do is you look at the information that they are giving you about how this is, what values you want to go between. So this says that I'm going between 6 and 8 minutes, and I'm going to shade the 6 to 8 minute on my table, actually, before I... That's okay, because it's not going to overlap, it's fine. So here's my 6 to 8 minutes. Okay, so everybody understand the picture first. You know where all the pieces came from, and you could recreate it if you had to. Okay, good. How can I find out what that little piece is? Because that piece isn't between standard deviation 1 and standard deviation 2, or standard deviation 2 away on each side, or anything like that. How could I find that piece of information?
Which piece?
The shaded piece. How could I find out how much of the percentage or probability of the data is between 6 and 8 minutes? Let me ask the question differently. What if I went between 6 and 10 minutes? How much of the information is between 6 and 10? It is. Where'd you get that, Abby? Yep. The empirical rule says so. 68% of the data is 1 standard deviation lower to 1 standard deviation higher. That's 68%. So what's that? Half. It's half of 68, right? Does that make sense? So this piece in red, and I'll write it in red as well, just for kicks and giggles, is 68%, and I halved it, which is what? 34. 34% of the phone calls are between 6 and 8 minutes. Okay, we can use this same picture for part B. Part B wants to know the calls that lasted less than 4 minutes. So where would I shade on this? Okay, this 4 and down, right. I would technically go all the way down. I mean, we could say it goes to 0, but you can just draw it sort of going towards the end of the curve as well. It's the blue part. So then, how do I find that area? Because you know what? This chart over here always talked about going back toward the middle, not going toward the outsides, right? Are you with me? So let me actually come back to this picture, and I'll draw it a little bit cleaner, and it might help us to see what we need to do without all the A's and B's and C's and such on there. So when I was looking at this curve, what we said is that 68% is here. And the next two pieces we had 95%. And then between the third standard deviations out, it was 99.8%. Right? Sorry, my picture's not all sort of, otherwise I'm going to write on top of words. I need to put an extra slide between those, I think. Okay, with this picture in mind, at the bottom here, this is 1 standard deviation, right? This is 2 standard deviations. And this one's 3 standard deviations. So far, so good? So, what if I actually went, out to the ends of the graph, wherever they end? How much percent would that be? It'd be 100%, right? So like if you think about this picture, the part here in the middle, let me use that red again, if this were shaded in, this is 68% in the middle, I could find the part outside of that, right? 68% in the middle, and then it would be 100 minus 68 for the part that's on the outside. We can use that same fact here. If you take a look and you use the blue as though it were right over here, these 2 pieces on the outside are in the part that's outside of the second standard deviation. How much is it between 4 and 12? 95%, right? Because that's 2 standard deviations out, 95%. So how much is it in the 2 blue regions on the outside? 5%. How did you get that? You subtract it. So what you're actually getting is you're getting 100%, that is the whole graph, minus that middle 95%. But we don't really have both blue pieces, do we? I mean, I shaded them in blue to give us perspective, but we really only had one of those. So yeah, just like Hannah was saying, we just really have half of that. We don't really have this part. So if you take 100 minus 95 and you divide by 2, you get 2.5%. So 2.5% of the phone calls are actually less than 4 minutes. I think there's one more on this. More than 12 minutes. Yes, it would. The more than 12 minutes would be the other half of the blue that I just erased, right? So it's the same. And you could find it the same way, of course, too. 100 minus 95 divided by 2, you have your 2.5%. All right, we're going to change data sets now. I'm going to pause for a moment and let you try to create the original bell curve with all the data points for the next piece given. It's about IQ scores. It says, the mean IQ score for 1,500 students, normally distributed, that's what lets you create the bell curve, got to have that in there, with a mean of 100 and a standard deviation of 15. So the only way we're going to be able to answer our questions is going to be to think about these empirical rule values we have. And in order to do that, I want you to start by filling in all of those particular values on your bell curve. And then we'll check and make sure everybody's matches. Okay, what number did you put in the middle? 100, because that's the mean, right? Let's go up from 100. What comes after 100? To the right. 115. And then I'm going to still go up. we'll go back to the downs in a minute. Yeah, no, I'm sorry. After the 115 to the right. 130, and then 145. Okay, now let's go downward to the left. Before the 100 was 85, like Rayleigh said. What comes before 85? 70, and then before that, 55. Okay, so this is going to be my chart for all of my problems. So I'm going to copy it so that I can highlight the different pieces and not overlap my picture. Okay. So the first question says we want to know how many students have an IQ between 85 and 115. So we'll start by shading that part of the graph in. So 85 to 115 would be that piece. So what percentage of the students lie in that area? 68%. Now, our problem's not really over because that's not really what it asked me for. What did it ask me for? It asked me for how many. 68% is not answering how many, it's answering what percent. So how could I take 68% and find out how many students that corresponds to? Yeah, you could do one of two things. You can remember that that would be a decimal of 0.68 and times your 1500. You could set up a proportion if you want to. 68 over 100 equals x over 1500. It's another way you've done it this semester. Either way, you get the same number of students. How many is it? It is. It's 1,020 students. Does that make sense to everybody? Okay. Part B says, how many students have an IQ over 145? Where's that? It's right here, right? Yeah, and we found that in a similar way, right? 145?
So it'd be 100 minus 99.8.
Yeah, it's not the 2.5 because but you're really close. It was the same way we did that, yeah. Okay, so it'd be 100. Hannah, what did you tell me it was?
Minus 99.8.
Yeah, minus the 99.8 because the information here is 99.8%. And then because I only want that top piece instead of the equivalent on both sides, I would divide by 2. So what does that give me? 0.1%. That is not the answer to my question. The question says how many students. So the first thing to do is to recognize that 0.1% is what as a decimal? 0.001. So I would need 0.001 times my 1,500 students. Or if you prefer, you can set up a proportion. It's 0.1 over 100 equals x over 1,500. Again, either way, what is this number itself? 1.5. What's the answer to my question? 2 students. Please don't tell me 1.5 students. Because which half are we going to take? Probably the half that includes their brain. Otherwise, the IQ part's not going to work, right? Yeah, so we don't have students. So round with normal rounding rules. If this had said 1.4, just round it down to 1, okay? So just normal rounding rules for this. Okay, one more question on this problem, I think. Right? Yeah? Okay. We are going between 70 and 145. All right, so 70 to 145. How are we going to do that? Because that's not like 2 below, 2 above. It's 2 below and 3 above, right? That's what it really is. 2 below, 3 above. So how are we going to fix that? There's several ways to do it, by the way. Shelby, did you? Okay, how did you get it, Rayleigh?
So 2
Okay, so let me. You're right. I'm just going to write it down so that everybody catches it. So the first thing she noticed is that if I went from 70 to 130, that'd be 2 standard deviations, and that's 95% of my data. Everybody good with that part? So all I need to really find is this little piece here, correct? If I can find that little piece there and add it on, then I'd be good to go. So how did you do that then, Rayleigh?
You just do 99.8 minus the 95, and then you divide that by 2.
So we took the 3 standard deviations amount and we subtracted off the middle 2 standard deviation amount, which gives me the intervals between 55 and 70 and 130 and 145. And then we divide by 2 just to get the part that's between 130 and 145. And you must have had 2 point something percent, right?
Yeah,
2.4%. So combining these together, you are correct. That's 97.4%. So we would have 0.974 times 1,500, or the appropriate proportion. And if I want whole numbers of students and so forth, how many students will I get? Mm-hmm. 1,461 students. All right, there's one more piece that we're going to talk about in this section before we call it quits for 10.4 and move to 10.5, and that is percentiles. A percentile shows a person's score relative to other scores. For example, a score in the 90th percentile means approximately 90% of all other scores are lower than this score. Can you think of a place where you've seen percentiles used?
doctor's office when they talk about kids' growth.
Very good, Hannah. I see that one used frequently too because I have children. So they get out these growth charts, especially when kids are young, and they make sure that their height and their weight give them a percentile that's relatively the same. So if their height's a really high percentile, their weight's a little low, they might actually be a little bit concerned, or vice versa with obesity, right? One of my children, Eli, the youngest one, we tracked his head circumference for a number of months, probably almost 3 years actually. When Eli came home from Ethiopia, his head circumference was too large. And so he had a mild case of hydrocephalus, which is water on the brain. It's never affected his cognitive abilities, but could have. And so they tracked his head circumference because they wanted to make sure that it at least stayed on the same curve as it continued to increase. They didn't want to see it increasing, more than what a normal sized child's head would be increasing. Okay? So he's still a little sensitive to the fact that his head's a little larger. His head's actually the same size as my husband's head. Your heads don't grow that much over your lifespan, actually, but it is the same size. So he wears like the same size baseball caps and stuff that my husband does. So that's a good one. There was another one. Did you have one, Alexi?
That's what I said.
Okay, doctor's office. Does anybody else know of another one? Grades. How so? Who said grades? Was that you, Hannah? How so? Where have you seen it used, like in the grading context?
Well, like getting into colleges and stuff, like ranking.
Okay, yes. So like your high school graduation, right? And that's actually the example I've got coming up here is about high school graduation and rankings. That's a good one. There's another one related to grades that you have seen before. Somebody said state testing, standardized testing in general. So usually scores are reported back in terms of how you did compared to other people, not how you actually did on the content. So 90% does not mean you got 90% of the problems right. 90% means that you did better than 90% of the other people who took the test. Now that's an interesting thing because that means you can't get 100, right? Because you can't do better than everybody else because you can't do better than yourself. So there is no 100th percentile when you're talking about any of this stuff. It doesn't make sense. There's also not 0 percentiles. But we can certainly have highs and lows on that. So when the kid gets their reports back and they're in the 80th percentiles or 90th percentiles, it means they're doing pretty good, or it means they're pretty tall, or it means their head's pretty big, whatever, okay? So that's how they're measuring things. Okay, cool. So we're going to do an example of this one, and it is going to be talking about how we think about percentiles versus the persons standing in their class. Junior was ranked 50th in his graduating class of 325 students. Liz was in the 75th percentile of the same graduating class. Which student had the higher GPA when they graduated? So they're comparing themselves in different ways, right? How could you figure out who actually had the higher GPA? Who's the better student? Who gets to go to college, right, Hannah? Which one of those kids? How do we decide?
Because of a proportion.
Okay, can you give me an example?
50 over 325 equals 75 over 100.
Okay, so 50 over 325 equals 75 over 100. How am I going to use this, though? 75.
Just multiply to see which one is larger.
Okay,
And then
so you want me to cross multiply. Okay, well, I don't know what 75 times 325 is.
24,375.
Okay, now what? First of all, you should be concerned about the fact that I just wrote that two numbers are equal that are not on the board. Is anyone concerned about that? Okay, so at the very least, we got to fix that problem. I think proportions are not a bad way to set them up, but I don't know that this is the proportion we want.
Would you put over the same number of people? 'Cause they're the same.
Ah, okay, so let's either, along that line, Amy, let's either figure out who was the first one? Where Liz was in terms of, is she the first, the second, the third, where she is in terms of her ranking, or let's figure out where Junior is in his terms of percentiles, one or the other of those. So let's just change one of them, though. We don't want to change both of them because that's too much change. We just need to compare. So do you want to change Junior into his percentile ranking, or do you want to change Liz into her class ranking? You want to do Liz? Okay. So Liz is in the 75th percentile. How are we going to turn her into her class ranking?
what 75% is of 325?
Okay, so there's your proportion, Hannah. 75% of 100 is something of 325. 325? Yeah, okay. So there's our proportion that we want. And if I cross multiply and simplify and so forth, what is the percent, or what is the x value that we get for this equation? We'll interpret it together, but what do you get for the numerical value first? 243.75? So write down 244 if you want. What in the world does that tell you?
Out of all of the 325 students, her grade average was 244, I think.
Close.
You subtract 244 from 325
Okay, why, Hannah?
to find where she ranks.
Okay, so let me take what you guys said and add one more piece to it. The 244 actually tells me how many people are below her. There are 244 people below Liz. So in sort of a picture, here's my 244 people, here's Liz. And what I really want to know is how many people are above her. So like what Hannah said, we're going to subtract, that's what we would do next. So we can get this piece by taking the 325 minus the 244, and what do we have? 81. So what this tells me is what about Liz? Yeah, Liz is 81st in her class. So who has the higher GPA? Yeah, Junior's GPA is higher. Okay, and there are other ways to do this problem where we would manipulate Junior's information to compare it to Liz's as well, if you wanted to do it that way. The Junior would have the higher GPA. Any questions on that?
If you were to have
Mm-hmm.
and you did like a portion or whatever,
Yep.
would it have been the same thing to where you would have needed to subtract?
Yes.
Yeah.
Yes, because in Liz's scenario, we were talking about the percentage of people below her, whereas in Junior's scenario, we were talking about the number of people above him. So yes, you've got to make amends for the fact that somewhere along the way there's a subtraction going on to get the comparison on the same side of their score.